Here today, one of the most unique neural networks that you should ever come across. This is a neural network built 98% on chaos theory. And so, if you know anything about neural network theory, kind of how I like to break it down and simplify it is that it always involves a linear process and a predictive process or a discrete process. And there's no way around this equation. That's what linear networks are based off of. It's linear to discrete or predictive, and or predictive to linear or discrete to linear. And you can play with that, right? You can use different math, and you can use different equations on different sides, and you can play with how much of each you have within that. And there's a lot of oftentimes what mathematicians will most often do is try to minimize the probabilistic aspects of a neural network, make it as linear as possible, and remove as much probability from the equation as you can, so that you can make it linear. And I decided, why not take the exact opposite approach and see what happens? Just why not, right? So let's make a model 98% probabilistic and like 2% linear. And then so how this model operates is all of the layers within the middle layers within the neural network operate within fractal space, and then so they operate via chaos equations. And the input layer is linear and the output layer is linear. And that's it. But if you know anything about this equation that we're looking at here, this very first equation, this Lorentz attractor equation, essentially how it works is any sort of like small perturbations whatsoever in an input will cause a massively different output. So if I put 1 in as the input, if there's any sort of noise whatsoever, because it's going to fractalize it, right? And then it's going to turn it out, and then the output could be 2, it could be 2.1, it could be -2, like it could be a lot of different things, right? And then so for this first equation, I test that. So let's put in a formula like XYZ, and then we'll what's the result of if we put XYZ as the output, what do we get, or as the input, what do we get as the output? And we get different outputs. We get sometimes a negative number, like this first one, -3.7 or 0.375, or it could be +2.34, +9.51, -2.04, etc. And then so there's no discernible pattern within this, right? It's pure chaos theory. And so within this, I mean, I flat out want to test a bunch of things within this. So my assumption and my hypothesis is that based off of kind of how chaos theory operates in and of itself, off of this probability mechanism, that we can, if we throw enough probability within this, it'll somehow start to operate in a linear sense. And that's the goal, right? So our goal within this then is essentially I want to create a neural network that operates off of 98% probability, but that produces a actual linear output. So if I put 2 + 2 into the machine, I want it to guess 4. I don't want it to do linear equations that come out to 4. I want it to the probability is 4. And so it's a very different form of math, and very different calculations, right? Number one is it's extremely fast, and that's the goal, right? Like I can do calculations via this method that I wouldn't be able to do via any other method if I can perfect it. is the goal. So number one, there's 2 tests within this. Number one is can it be done, and then number 2 is can you dial it from there. If you can prove number 1, then number 2 is an inevitability. It's just a matter of figuring it out from there. So we'll test and prove within this video, can we actually do this? And I'll show you that you actually can. So let's go through. And so this first one was just a test, right? We're taking our input and we want to know, will it actually get a result. And we see it does get a result here, which is kind of crazy. So let's take this a step further then, and let's build our actual our first iteration of our beautiful mind, our chaos theory driven neural network. And then so within this, the very first thing that we do is I want to classify exactly what this is. So it's the chaotic layers that operate within it. And then it's going to operate off of feed-forward mechanisms of forward propagation, as well as back propagation. And then so within that, we're going to use the Lorentz attractor, as we did for these straightforward mechanisms. So it's chaos theory is built into this model. It's essentially its framework is chaos theory. And then so we need to build chaos theory into it. Right? So that's exactly what we do. And then so here's all of this, all chaos theory built into a feed-forward mechanism, and then that's how this model does. This model only operates, its entire feed-forward mechanism is chaos theory. But then remember, at the top of the video, I said no matter what, every single neural network, and you can't get away from this, you need a probabilistic layer and a linear layer. So we have a linear layer in our neural network. We have one linear layer, right? This right here is the code for our linear layer. All the code that we went up, all of this, blah, 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 that's all for the probabilistic layer right here. And then those three above it are comments, the comments for the 3 lines. But these 3 lines out of this entire code base right here, these 3 lines right there, that's our linear layer. And so we need a linear portion, right? So we have it. We got that. Oh, not that third one. Sorry, just these 2 here, right here. These 2 are our linear layer for the entire neural network. And then it's basically saying that the input is linear, that the input will be linear. Oh, and the output will be linear. So here and there and here. So three lines total. Cool. And then the rest is all here in between. We've got more chaos theory, right? So sandwich all around these 3 lines of linear code are just straight up probabilistic math, and then 3 lines of linear algebra. And then, so we go through, and then we need to define we need to calculate it via linear algebra. So we do that. And then same thing. So our calculations are all linear. Once we get and we define all of the probabilistic setup, so it's 5% linear. Maybe this model, let's give it a little bit more credit there. And then so we train it, and then the first thing here, first of all, ignore this first training loss, because it's bloated, because if you go through this code, what you'll see is in this first test, I train on the test and the train set, and then so testing on the training on the test set will give you a low loss rate. Go figure. And then so, but it's not going to actually increase performance when it comes to actual predictions. As we can see here, which is interesting, right? So we get over 500% mean squared error. Means that these predictions are way off. But if you look at the predictions, they're varying and they're doing something, right? It's not just saying 1 is the prediction every single time or something like that. It's learning something from these progressions, and it's taking data from it. So test number 1 is successful, right? And I'm just taking in this test 1, I'm taking one dimension of this. I want to know will it actually do something? And a failure in this test would have been that the loss rate doesn't go down, it doesn't learn anything, and that the predictions would all be the same, all 1s or all 250 or all something, right? But deviations in the predictions, the loss rate going down, these are this means that the model's learning. And then so 518% off, that's fine. So we need to get this number down now as our next play. So I work on that. And so I essentially just do that by adding some more math, adding some more chaos theory into here, and then adding a few more functions. Really, overall, is really what we're doing, right? And then so that's the main difference. I train it a little bit longer, as you can see here. I train it for 1,000 epochs, and then I don't train it on the test set again, and then what ends up happening is we get this crazy loss rate to start off with, 355,942, and like, that makes me like gulp, like, okay, like I've never seen a loss rate this high, like I don't know if it's going to actually do anything, but I train it down and it trains down, right? Like, so like again, the loss rate is that's an astronomical loss rate, but ignoring that, the model is learning. It goes from 355,942 down to 207,276. Massive decrease, right? Like 150,000 loss points of loss over 1,000 epochs, which is significant, right? Like very significant. In that, like 1,000, it's a dropping like 1,000 points of loss every epoch. Kind of crazy. 10,000, and then 1,000. So, and then we end up like again, these numbers end up like still pretty randomized to me, but again, that's different. They're differing numbers, right? So it's not, it's calculating something, and then our mean squared error goes down 173. Like starting at 500 and then going down to 173. That's pretty good. We made some progress. So it can means we're pulling the right lever. If I pull this lever more, is it going to do more, right? All of this is, so if none of this were actually working, if I were pulling these levers, nothing would happen. And that's kind of our test, right? So then our final test, we've got it down and we proved that this lever exists. We proved that we pull this lever, it goes down. So 173. So can I pull it more, right? Like, so, I mean, let's just prove it out fully, that there's full causation here. And then so what I do in this last test is I've been using the Lorentz attractor for our fractal space and all of the other ones. Essentially, I create two other fractal spaces, and then let's test. That's really only the major difference, right? And I'm just giving it more features, more fractal space, more chaos, and more chaotic places and more chaotic spaces to play within and to function within. Other than that, all the math stays the same. We still got like those 3 linear lines total. And then so I also add a early stopping mechanism, because I noticed like at a certain point it's not the loss rate is going down. The loss rate will go down with this model, I noticed, forever. But I don't want to train it forever. So if the loss rate starts like, if it's going down like less than like 300 per turn, that's where I kind of like cut it off. And then so in this instance, we get that crazy amount again, right? Like 511,555, and I train it down, and then it goes down, right? So 508,480. As long as it's going down, like I mean, 500,000 loss rate. That's pretty absurd, and that's pretty crazy. But it's going down, right? So it's going down, meaning that there's something that the model is learning from and then predicting in here as well. And then like we get completely different predictions in this instance as well too, right? And then like and then as we can see, we're within the ballpark now, 98%. So like we pulled this lever again, and like so we've proven this lever exists and that you can pull this lever. And then so if you can pull this lever down, and if you could pull this lever down more and more, you'll get exactly the model that we want, right? And then so I try it again. I try it one more time to pull the lever, and I make a little bit of progress. But this time, I'm kind of like maxing at this point as to how much I can pull this lever. And I mean, flat out, I set up this experiment not knowing if it would work, what would work, right? I just thought like, I want to see what would happen, like, because I know like just most people, they build out a model that's like 98% linear, and then I see it in the models that I deal with all the time, and it kind of clicks in my head a lot, and I think about it a lot. Like, man, like they're really limiting the probabilistic aspects of the model, and to me, I think it's just important. I think the probabilistic aspects of this are important, so why not put that to the test and then do the opposite, right? So, man, let's really limit the linear aspects of this model. Do the exact opposite of what anybody would want to do. See what happens. And hey, we're getting something here. And then so again, like if you can get if you can get this down to a manageable level, like single digits, what you end up with is this last one. This runs super fast, right? So in this last one, I cut out all sort of overhead, and then so it's just computing the math, and it's computing the math for very hard problems, and then but it's computing them very instantly because it's guessing. And then so essentially like problems that are unsolvable right now or that take way too much compute time, you would be able to utilize this flat out like a quantum computer and be able to make like quantum calculations, right? That's if you get this down to where it actually works. It's working right now, but like to where it's like those equations are actually fully useful data for you, then like that's what this will do. And I've proven up to this point that you can pull the levers down to that point. I just don't know how to pull the levers down to that final point, right? But if you can, I'll leave all this code in the description. Feel free to play around with it. But if you can get these levers down, this is like here it is, right? Like, and it would be, you take the most complex equation that you can possibly think of, you throw it into this magical digital box, and then it's going to spit out a probability equation. Like, and it's going to be, and the probability equation, if you get this mean square error down, will actually be like the probability of the equation. It will be the answer, and it will be the answer like that because it's guessing the answer. Instead of going through linearly. So really cool how this math works, right? I mean, so for ever since I found out like probability exists, game theory exists, this has been kind of my entry point and gateway into these things. So like I understand it's hard to understand the mathematics of neural networks. A lot of the mathematics are built hugely on chaos theory, and then so like people try to understand or figure out like how have I been able to understand or how do I understand the math of this so quickly, etc. It's because of my base of chaos theory, right? If you've known, like for 20 years, I've debated chaos theory. I was a debater in college. I utilized chaos theory extensively there, and I've studied chaos theory extensively, John Nash theory, really extensively ever since I was a kid, and the quantum, like how it ties to quantum mechanics and all of that. And then so that's my foundation within this, and why I like to play around with this. Like kind of like my bottom line, honestly, is like I think that my approach is that via chaos theory you can control probability. Let's say like 4 to 5%. Let's say that like there's like a luck equation that exists, right? Like a general luck equation. And that's kind of what chaos theory represents to me, and what you can play around with. And if you study chaos theory extensively and you get like really good at chaos theory, you get to turn that luck equation 3 to 4%. Like as a dial, right? And 3 to 4% of I'll take 4% luck, more luck every time I try, right? Why not? And then so that's why these things come in. But then so utilizing and building off of these into neural networks, because that math gets built into these these neural networks would not exist without that math. And then so understanding that math, understanding those concepts, and then being able to play around with it, you get really cool things. And like to me, this is the most counterintuitive concept that you could possibly think of, but I prove it exists. Like this concept exists, meaning that through enough probability, if you throw enough probability at something and you figure out the probabilistic equations, you get a linear result, because there's a correlation between linearity and probability. Like there's a connection, right? Which is why you always need both for neural networks. And so I'll leave this here because I'm getting further away from the math and more into philosophy. But so if you like this type of content, please like and subscribe. Thank you very much.